Good afternoon, everyone. My topic for today's session is Bacterial Foraging Optimization. Here are my contents: introduction, basics of BFO, then optimization steps that are followed in this optimization technique. BFO has many applications as in comparison to all other optimization techniques, but mainly I'll talk about BFO as a denoising filter and will work on this area. Then the flow chart of this optimization algorithm, its advantages and applications. Starting with all these techniques which we are talking about here today, optimization techniques, BAT algorithm, PSO, BFO, and fuzzy logics, they all come under the concept of soft computing. Why do we need soft computing? For the systems with imprecision and approximations that cannot be modeled and examined with the already available mathematical tools, we go in for soft computing. Now, soft computing, what it do? The techniques in the recent past, they have been developed for denoising filtering, denoising the image and denoising filters. I'll basically take the example of human body, and for denoising filters, there we require for managing the for getting treatments of the various medicine in the medical domain for treating various diseases. For that we need denoising the image, and for denoising of image we need a denoising filter. Adaptive algorithms along with denoising, they perform well when we use optimization techniques. Now, talking about introduction, BFO is a nature inspired technique to find the optimum solution of the problem. In 2002, Professor K.M. Passino, they introduced the optimization technique known as BFO, which is based on the social foraging behavior of E. coli bacteria that is present in human intestine. Now, social foraging behavior, it refers to the foraging technique, that is the search of food. Bacteria, they'll move into the direction of the increasing nutrients. Here in case, when we related with the image processing, the cost function will define as the minimum error. Mean square error, that is the cost function, it has to be minimized. The more it is minimized, the more fitness function we get there. Now, bacterial search for nutrients in a manner to maximize energy obtained per unit time. The total energy it is gaining from the nutrients per the time it has utilized the time for searching that nutrition direction, that is the optimization parameter. Maximization of such a function provides nutrient sources to survive an additional time for the activities that are required to be done by the bacteria. This formulates the foraging problem as an optimization problem. Now, relating it with the image processing systems, we need the image pixels and to move it in a direction where we get less noise and more of the fitness values. Individual bacteria, they communicate with others by sending the signals. During foraging realization, the real bacteria, the two basic operations are being performed: swim and tumble. This will be covered in the first step of the foraging optimization. Now, the basics. The bacterial foraging is an evolutionary algorithm which estimates the cost function. The cost function in this example for denoising the image which I have taken is our mean square error minimization. We have to work upon that. After each iterative step, as the program proceeds, it leads to the progressive better fitness. Better fitness means less cost function. And the parameters to be optimized, they represent the coordinates of the bacteria. We can talk about bacteria in case of human intestines or the optimization technique BFO, but when we relate it with the image processing, we'll actually take the coordinate system, the search space area where we need to minimize the error function and optimize our cost function. The parameters are the coordinates of the bacteria, that is the position at which a pixel will be placed. The parameters, they are discretized into the desirable range, and each set the values they represent in the space coordinate systems. The one bacteria is positioned. Now, the complete search space area which will have at each position will have one bacteria, and after each progressive step, the bacteria, it moves to a new position, that is new coordinate system, depending upon the when in comparison to the previous pixel value, if the cost function is less, it will tumble, it will change its direction. But if the fitness value is not that less, cost function is same or either more, then it will not make a movement to that direction. and at each position cost function is calculated. With this calculate value, further movement of bacteria is decided. Means the cycle goes by, first we initialize certain parameters, then we check the cost function, and after every checking of the cost function a movement will be made by the bacteria, and after that step movement again the cost function will be evaluated till the complete search space in the coordinate system is being completed in that manner. This finally leads to bacteria to a position with highest fitness. Now, comparative to all the pixels in an image, it will make comparison or movement in the complete search space coordinate system, and it will reach to a position which is the highest fitness value. There are 4 steps. First is chemotaxis step. Second is swarming, reproduction, and elimination. Now coming on to chemotaxis step, this is achieved by swimming and tumbling. Now there are 2 processes in chemotaxis, means movement what the bacteria will make. Either it will swim or it will tumble. What is swim? A unit length in the same direction, it refers to swim. If a unit walk in the different direction or as in comparison to previous direction, that is called tumble. Now, when the bacteria it meets a favorable environment. In case of bacteria, the favorable environment is the direction that is increase in the nutrients and noxious free. And in case of pixels or images, it is the pixel value that has less of error value as in comparison to the previous pixel values. It will continue swimming in the same direction if the nutrients increase in the direction of swim. It will swim in the same direction. Otherwise, if the nutrients are not increasing, it will tumble. These are the 2 steps, and the bacteria it keeps on operating between these 2 positions in its entire lifetime. This is the chemotaxis step. Swarming. E. coli bacteria, it has specific sensing, actuation, and decision-making mechanism. In each space, in each coordinate system, each bacteria it coordinates with other and decides for the local and the global based fitness functions. As each bacteria moves, it releases an attractant to signal the other bacteria and to swarm towards. Swarm is like grouping. It will signal to the another bacteria and they will group together and move to the next better position. Reproduction. After calculating the fitness value for each bacteria, reproduction allows the half-healthy bacteria to survive and reproduce. This is the main important point which leads to many applications and advantages of this very optimization technique, since it reproduces and it cuts short the very half unhealthy bacteria whose fitness value is less, and now we have to deal with only the left half of the bacteria, and those half bacteria they are already having more of the fitness value. Hence, this leads to the advantage of fast convergence. This helps in generation of values of variables which are close to the actual values. Now, once we have deleted the unhealthy bacteria and working with the left of the healthy bacteria and their reproduction and elimination, this will lead to the results that are closer to the actual values. 4th step in this optimization technique is elimination and dispersal. Now, elimination, the chemotaxis provides basis for local search, and reproduction, it speeds the convergence. The first 2 steps that we have talked about, the first step, it provides the local search, and the reproduction, it speeds up the convergence, as I have told. Now, why is elimination and dispersion required? To avoid the trap of bacteria in the local minima, elimination dispersion is done. If a bacteria will compare into a certain limited area, it might get trapped into a local minima. But we have to eliminate it and disperse it. In dispersal, what happens? A single bacteria, it gets divided up into 2 similar bacteria. Hence, the overall coordinate systems, it is equated with the same number of bacteria, but with the healthy one. Now, using BFO as a denoising filters, why do we need denoising? I'm taking here the case of, like in example, medical images. We require more optimized results, less of noise, so that the treatment can be done. We use denoising filters, and to denoise it, we need algorithms. BFO is one of the best that is applied in that case. It presents a soft computing approach to denoise the medical images. This is a bio-inspired algorithm that is used as a filter. Hence, we are talking of BFO being used as a filter for denoising. Requirements in the medical images. Like in medical images, the noise inserted are very miniature noises. Even the noise from a signaling to the bones signals to the brains, and the body movements, they can also cause noise and interrupt with the actual or the targeted value of the image that we require to diagnose in that case. And we need to be eliminated for the better diagnosis. Now for soft computing techniques, as I've told, they can either work in isolation or in conjunction with filters. Those filters can be either adaptive, median, or adaptive median filters or average filters. Basically, they have told here that with gradual Gaussian noises, BFO is used in conjunction with median mean filters, and other type of noises like salt and pepper noise, BFO is used in conjunction with adaptive median filter. It gives the capability to search the pixel without jumping or skipping. Now, one more advantage of BFO which we'll talk about is its accuracy. Now, how this accuracy comes, since the just like in case of the bacteria, it moves and does not jump, but it covers all the pixels one by one, thus it improves the quality of the image that we require. BFO is a soft filter for taking the diagram. This is adaptive median filter. We take a noisy input, pass it through the adaptive median filter, we get the output. This output to the median filter, it has reduced some noise, but not to that extent that we require. Hence, we subtract it from the original image and get the error signal. This error signal is used as the basis for bacterial foraging optimization, which will make updates for the weights, or either it can make it adaptive in the manner that it can increase the area of the swim. This will take up in the advantages. Now this error signal has reached up to, it has gone to, now first was our input noise that has gone to the adaptive median filter. This noise is subtracted from our original signal. Now this error signal, this is the signal that was not being removed by the adaptive median filter. Adaptive median filter was not able to remove this error. This has gone to the bacterial foraging optimization technique that will optimize its weight functions or its coefficient in the parameters, and then again it will move on to the median filter, which will again denoise the image and give the output to the original signal. In each time the bacterial foraging optimization is applied, in each iterative step, more number of clarity, more number of noise reduction, more amount of fitness function will be achieved each time. This was the case. Now ideal images, they are corrupted with noise. Noisy images pass through adaptive median filter. Difference in terms of mean square errors. This difference we do not take just simple difference, as earlier also in PSO we have studied. We take the mean square error between the filtered image and the original image. This is our cost function, and less amount of this cost function, more is the fitness value. Now to further go to the BFO algorithm, we have to initialize certain parameters. This algorithm, how much hectic it might seem to be when it comes to presentation, but there are basically 4 to 5 steps. First is initialization of parameters, then is evaluation of the fitness functions. Once we have evaluated the fitness function, we'll make a movement. That movement will either be a swim or a tumble, depending upon either the cost function is less or the cost function is more. After that, what we'll do, we'll check the swimming steps. We'll set a counter initially, because initially the bacteria has made no movement. Now if this is our search space, initial bacteria, this is ith bacteria, it is starting from here, this is set to 1. I equals to 1 will initialize this parameter. For each bacteria, for I equals to 1, we will keep on increasing the J parameter. J parameter will take as the chemotactic steps. For each step, here is the chemotactic step NC. NC. For each increment of I, again J is all the chemotactic steps will run, and till the time it is less than NC. This loop will run till the time J is not equal to NC but less than NC. Will again compute for all the next position, that is I will be incremented by 1 now. And then similarly chemotactic steps, now this number of swimming steps will initialize. Number of reproductive steps will check how much bacteria we have got for the fitness values, eliminating that and reproducing the healthy bacteria. Number of elimination and dispersal steps, that is NED, and the probability of elimination and dispersal. This is the variable. The number of bacteria that will die in this range, they will be eliminated and the equal will be dispersed in the coordinate space system. Now the cost function which we are dealing with, which we have to minimize in this optimization technique, is MSE, that is mean square error. This is this cost function. 1 upon mn summation of this f dash, this is the filtered output. The output at the adaptive median filter that we have received, subtracting the target image and squaring it. This is the mean square error that we need to minimize. Now we have taken the filtered output as f dash xy and f a function of xy. But for the case of the pixels, now pixel to pixel operation is to be performed. Now we have to change these parameters. We'll take it in with respect to p of I, j, k, l. 4 parameters will be included now. It will depend upon 4 values. Similarly, this was for f dash xy. For f of xy, this will be r, x, j, k and l. But now what is PIJKL? This refers to location of ith pixel, j is the jth chemotactic step, k is the reproduction step and l is the elimination step. Similar way, in our algorithm will go by these 3 loops. One will be reproduction loop, other will be elimination loop and first will be chemotactic steps. Once we understand all these parameters, their initialization, then algo becomes very easy to understand and implement. For the function fxy, we have taken it r. This is x is the target pixel. Now I was our simple location of the pixel that will take at the starting of our coordinate search space system. X is the target pixel which we need to make it equal to. Z is again same chemotactic step. K is the kth reproduction step and L is the elimination step. Now instead of using this MSC value which we have used here, this MSC value will update this with the pixel values. This one, this function will use now. Now this is J will represent the cost functions, P of I will represent the adaptive filter outputs and this R will represent the original values and mean square is the whole square value. And j will represent the cost which we have to minimize it. This is j value, this is the cost function, cost of the pixel, and ci, one more parameter that is initialized is c of I, that is step size in the random direction. This is the algorithm. Step 1, we'll start the algorithm, we'll initialize the parameters p, s, nc, nr, nd. What is p? Is the search space, this is taken to be 1. S is equals to m into n, that is total pixels in our image. NC is number of chemotactic steps, NRE is number of reproduction steps and NED is elimination and dispersion steps. Now initialize I equals to 1. What we have to do after initialize, we have to compute the cost of the bacteria. J we took it as the cost. Now we'll make the difference between the output and the target image value. Clear? Now the J last will be updated by this difference value which we have calculated. We'll update this value into J last, a variable. Now tumbling means we have taken up the next chemotactic step if it tumbles. This is also the difference and mean square value. Now, after making a tumble or swim, we have to initialize a counter that will take care of how many tumbles or swims it has made, setting m equals to 0. Now, if we'll compute, if the ji of 1 which we have find out, if it is less than the last calculated value, the bacteria makes one more step in the direction of tumble. Clear? It will make a change if the value cost function, j is the cost function. If this cost function is less, it will make a move in the direction of tumble. Now one direction has been made, we'll increment this with 1. Earlier this was 0. Now if we'll calculate if m is less than n is. Now this counter, if we'll check it for number of the swimming steps, ns is the number of swim steps. If this becomes less, then we'll again compute for the cost function value Otherwise, we'll check for the I. I refers if all the pixels, all the bacteria have been checked in this space. If I has completed all this value, if I has reached the search space is ended, we'll end this. Otherwise, we'll increment I will be next I to I plus 1, next value of the bacteria. After that, it will go to step 3. Step 3 here is again computation, tumbling. Now one more thing which here I want to tell, like for any function value, we'll take j plus 1 will be what? J, this is K, this is L. Next chemotactic step will be equal to what? This will be equal to previous chemotactic step, that is J, comma K, comma L, plus the Ci. Ci was what? It was the step size of the swim, or about what area the bacteria is making a swim. These earlier position and the Ci position, these two positions combined will give the new value for the chemotactic next step. Now increment, if I has been checked, if all the bacteria are covered in this search space, now what will it look for? It will look for if all the J, that is the chemotactic steps are, it will be incremented by 1. First chemotactic step is over for ith bacteria, then second step, then third step, and then it will increment bacteria. Now, this was the previous result. I will settle for 1. Compute J health. Now, in these two slides, what we have covered, this is like initialization, initialized, evaluated. This is made a tumble or swim. This has updated its location, new location value. And coming on to here, the third and the fourth step will be performed now. That is reproduction, and this is elimination and dispersion. After the healthy bacteria has been calculated, we'll again check it for it has reached completed its search space or not. Now this is sorting of half of the healthy bacteria and half of the unhealthy bacteria. With this step, we'll now reach to K. K was what? Reproduction step. If half of the unhealthy bacteria have been deleted from the complete group of bacteria which we are talking about, we'll increment our reproduction step again. If now after each increment we have to check it for these 4-5 values which we had initialized, these values NC, NS, NR, NE, ND. After each increment we have to check these. Now it has incremented for K. It will check if K is less than NS or not. If it is less, then it will lead to a 0 value. Otherwise, again starting with the first pixel, it will eliminate, check for its elimination has ended up with the entire search space area, and then it will increment L, that is elimination and dispersion. Finally, if our L is also less than ND, that is number of elimination dispersion steps, if L is also less than that, will return the bacteria with the lowest value of the cost function. That was actually the main aim of the foraging optimization technique over here, and then end the complete system. Now talking about advantages, less mathematical complexity. It might look big when we talk about the complete flow diagram, but there are basically just 4 steps which we have talked about: NS, NC, NRE, and NED. Fast conversion, since we eliminate 50% of the unhealthy bacteria, accuracy and widespread applications. BFO is largely not affected by the size and nonlinearity of the problem. This is also used in fact EC devices. Like we can talk about it as being used in image processing. It is on the parallel being used in the terms of electrical, like students, they can also use this optimization and they work upon for their thesis because it is used in fact devices. These are flexible asynchronous transmissions. For fact devices, there is large scope nowadays, and there's also uses optimization techniques like BFO, which we are talking about. It converges to the optimal solution in many problems where most analytical method fails. I have quoted some few papers in which they have proved it with all the analysis that BFO and adaptive BFO, these both techniques are much more optimal solution providing than in comparison to generic GA and PSO algorithms. Applications. It has drawn attention of researchers as a high performance optimizer, and it has successful applications in following areas. It is used in PID controls, hence we can say it is optimum control engineering. Image processing, like denoising filters for human intestines, it is present, we'll use it as denoising of the many diseases. Network scheduling, it is used in electric load forecast. BFO coupled with methods of movement, MOM, it has also been used in antenna applications. Nowadays, many antenna applications are employing these optimization techniques, and even in fact devices. MOM is method of means, moment of means. The moment of means is, it is basically the average power of each random variable. We decrease that power in the random variable and make it optimized. The first application is SABFO, that is self-adjusted BFO. This is a variation of BFO only, and it works much more accurately than BFO when applied to RFID, radio frequency identifications, network scheduling. The simulation results when compared to GA and PS approved superior solutions. With each of the application, I have mentioned 7, and with this 7 references from where the papers these have concluded. Applications of bacterial foraging optimization, it is used in neural networks. In the starting I told it is used in all the soft computing techniques using fuzzy logic, neural networks, artificial intelligence. For short-term electric load forecast, simulation results also showed BFO converges more quickly than this is generic algorithm neural networks. It converges, it takes much less time as compared to GA neural network. BFO is applied to antenna problems. In antenna problems, how this is applied, it optimizes the directivity, taking inverse of it as the cost function. We need to minimize the cost function. It takes directivity as the inverse and do the optimization. It is capable of synthesizing patterns with multiple nulls at desired directions, that too with fast convergence. Again, this fast convergence, and this is used in antenna applications where we need the multiple nulls at a desired direction so that beam width does not spread and we get high bandwidths. It is used to calculate resonant frequency and feed point of microstrip antennas, which many people are working on. This is also using BFO as its optimization technique for the thick substrate values to make the frequency in resonance with the actual input frequency. It is used in image enhancement tool for reconstructing high quality of images in less times. In fact devices, this is used in achieving the minimization of the real power loss. The total power loss in the devices at the transmission sites we need to be minimized, and this is the fact devices BFO is used with total cost is also minimized, voltage profile is improved, and voltage stability is being achieved so that transmission does not cause a problem to even the longer distances. Now, these are certain references for RFID. This was RFID network scheduling used in adaptive bacteria foraging algorithm. This was in one of the journals of computer sciences. And bacterial foraging optimization for neural networks, which we have talked. For dipoles of high directivity in antennas, and convergence antenna array faster convergence, and rectangular microstrip antennas, and these are the adaptive filters to enhance the signal to noise ratio in an image. Thank you.